Hello guys, welcome back. Today we're going to talk about AC motor controls part 8, automatic acceleration for wound rotor motors. We're going to talk about the advantages of using controllers to provide automatic acceleration of wound rotor motors. We're going to talk about the identification of the terminal markings for automatic acceleration controllers used with wound rotor motors. We're going to talk about the process of automatic acceleration using reversing control. We're going to talk about the process of automatic acceleration using frequency relays. We're going to talk about how to connect the wound rotor motors and automatic acceleration and reversal controllers using push buttons and limit switches. Secondary resistor starters used for the automatic acceleration of wound rotor motors consist of an across-the-line starter for connecting the primary circuit to the line and one or more accelerating contactors to shut down resistance in secondary circuit as the rotor speed increases. The secondary resistance consists of banks of 3 uniform Y sections. Each section is to be connected to the slip rings of the motor. The wiring of the accelerating starters and the design of the resistor sections are meant for starting duty only. This type of controller cannot be used for speed regulation. The current inrush on starters with 2-step of acceleration is limited by the secondary resistors to a value of approximately 250% at the point of the initial acceleration. Resistors on starters with 3 or more steps of acceleration limit the current inrush to 150% at the point of initial acceleration. Resistors for acceleration generally are designed to withstand 1 10-second acceleration period in each 80 seconds of elapsed time for a duration of 1 hour without damage. The operational accelerating contactors is controlled by a timing device. This device provides time acceleration in a manner similar to the operation of primary resistor starters. Normally, the timing of the steps of acceleration is controlled by adjustable accelerating relays. When this timing relays are properly adjusted, all starting periods are the same regardless of the variation in the starting node. This automatic timing feature eliminates the danger of an improper start-up sequence by an inexperienced machine operator. The primary circuit is energized with a start button. The motor starts with a full value of resistance in the secondary circuit. Coil P actuates the normally open delay in closing contact P. After a preset timing period, contact P closes. The energized contactor S1 and maintains itself through the maintaining contact S1. When contacts S1 and the secondary resistor circuit close, the motor continues to accelerate after the normally open delay in closing contact S1 times out and closes. Contactor S2 is energized and closes the resistor circuit contacts S2. The motor then is accelerated to its maximum speed. The normally closed interlock S2 opens the contactor S1 circuit. The closing of S2 is assured by staggered or overlapping controls, contacts, S2. Automatic acceleration or reversing control. Automatic acceleration can be obtained in either direction of rotation with the addition to the circuit of reversing contactors and push buttons. As described for a squirrel cage motor, a wound rotor motor can be reversed by interchanging any two stator leads. The motor may be started in either direction of rotation at low speed with the full secondary resistance inserted in the circuit for either direction of rotation. The timing relay TR is energized by the normally open auxiliary contacts F or R. Coil TR activates the normally open delay-in closing contact TR. Coil S is energized when contact TR times out and closes, and removes all of the resistors from the circuit to achieve maximum motor speed. The primary contactors are interlocked with the push buttons. Normally closed interlocking contacts are in F and the mechanical devices. The connections that occur if a limit switch is used are seen in the by dashed lines in the above image. The motor will stop when the limit switch struck and open. In this situation, it is necessary to restart the motor in the opposite direction with the push button. As a result, line 1 and 3 on the primary side will be interchanged. Of course, if limit switches are used, the jumper wire must be removed to avoid shunting out the operation of limit switches. Automatic acceleration using frequency relays. Definite timers or compensated timers may be used to control the acceleration of wound rotor motors. Definite timers, which usually consist of pneumatic or dashpot relays, are set for the highest loads current and remain at the same setting regardless of the load. The operation of a compensated timer is based on the applied load. In other words, the motor will be allowed to accelerate faster for a light load and slower for a heavy load. The frequency relay is one type of compensating timer. This relay uses the principle of electrical resonance in its operation. When 60 Hz AC wound rotor motor is accelerated, the frequency induced in the secondary circuit decreases from 60 Hz at zero speed to 2 or 3 Hz at full speed. In the above image, the voltage between the phases of the secondary circuit decreases in the same proportion from zero speed to full speed operation. At zero speed, the voltage induced in the rotor is determined by the ratio of the stator and rotor turns. This action is similar to the operation of a transformer. The frequency, however, is the same as that of the line supply. As the rotor accelerates, the magnetic fields induced in it are almost match the rotating magnetic field of the stator. As a result, the number of lines of force cut by the rotor is decreased, causing a decrease in the frequency and voltage of the rotor. The rotor never becomes fully synchronized with the rotating field. This is due to the slip necessary to achieve the relative motion required for induction and the operation of the rotor. percentage of slip determines the value of the secondary frequency and voltage. If the slip is 5%, then the secondary frequency and voltage are 5% of normal. The above image illustrates a simplified frequency relay system operated by a push button starting. This system has two contactor coils connected in parallel, A and B, and a capacitor connected in series with coil E. A 3 steps automatic acceleration results from this arrangement. When the motor starts, full voltage is produced across coils A and B, causing normally closed contacts A and B to open. The full resistance is connected across the secondary of the motor. As the motor accelerates, the secondary frequency decreases. This means that coil B drops out and contacts B close to decrease the resistance in the rotor circuit, resulting in continued acceleration of the motor. The capacitor depends upon the frequency of the alternating current. As the motor continues to accelerate, coil A drops out and closes contact A, accelerating the motor further. Because the normally closed contacts are used, the secondary of the motor cannot be shunted out completely. If the secondary could be completely removed from the circuit, the electron flow will take the path of the least resistance, resulting in no energy being delivered to the coils A and B upon starting. The controllers for large crane hoists have a resistance, capacitance, and inductance control circuit network that is independent of the secondary rotor resistors. Frequency relays have a number of advantages, including positive response. Operating current drops sharply as the frequency drops below the point of resonance. Accuracy is maintained because this type of relay operates in a resonant circuit. Simple circuit changes in temperature and variations in line voltage do not affect the relay. An increase in motor load prolong the starting time. As always, thank you guys for watching, and please, if you like my videos, like, share, and subscribe. See you in the next one.